Thank you very much for this kind introduction. Good morning, everyone. Good afternoon to people probably somewhere in the world watching this presentation. So, following suggestion by Professor Yakovu, I will start with the conclusions. So, the first conclusion is AI is very energy intensive. So, probably more than 50% of the energy that is consumed in all of the AI systems, hopefully I will illustrate in this presentation, is that algorithmic inefficiencies. So, some point in the future, probably 2050, close to 50% of global energy demand, if the recent trend continues, is going to be fueling artificial intelligence.
اصلا انا عملتها عشان بفطر بيها وبعدين كنت عايزه تستوي شويه كمان.
Mute, please. Thank you.
Thank you. So 50% of global energy consumption by year 2050 could go to AI. The majority of this is due to algorithmic inefficiencies. Hopefully I will illustrate it. So my take and my approach to this problem as a responsible researcher in algorithm design and also process systems engineering is to spark in your mind as future leaders in this area, what could we do? What can we do to change this situation? Because this is catastrophic. 50% of our energy is not going to be improving our lives, but indirectly AI is going to improve, but we could do better. So I'm going to illustrate this. This is the main take-home message. Second is going to be a small application that I want to illustrate the impact. It is not 100% artificial intelligence yet. We are still working on it, but I am mainly going to illustrate the main model development, so what it takes to develop models for artificial intelligence-based applications. So, after giving you the reasons why you should listen to this talk, so here's the outline. Outline is motivation. Okay. How AI works, and I received a lot of help from you. I asked ChatGPT, how do you work? Now pictorially, I'm going to use artificial intelligence to show you how it works according to AI. Then I'm going to follow up my most recent presentation here on a summary of AI and energy. Why AI needs this much energy, or how do you project this energy? And probably this is going to set up and spark ideas. We should do something to change this, course of events. Then I'm going to focus on AI training problems. Maybe some of you have taken courses on AI or machine learning. Majority of the effort in this area goes into model identification, model development, or training problem. So what is the core algorithm that is used in training any artificial intelligence-based methods, artificial neural networks included? Then activation functions. So, some of you who has taken the optimization course from Professor Christopoulos will immediately recognize that these algorithms, training activation functions, are something that we know very well. So, how do we solve this? And I'm going to introduce an alternative approach to change the core algorithm of training problem in artificial neural networks. And recently, maybe you have listened to Yann LeCun who is the founder of deep, learning, he said that, we have invested so much in generative AI and the result is stochastic. It doesn't give you the answer all of the time. Same input, different answer, because it is the stochastic nature of the solution algorithm. So you ask artificial intelligence one question, today it answers something, and tomorrow it answers you something else. You see, this is a problem. This is a problem. This is a well-documented, well-recognized. So how do we eliminate these problems? So it always at the core, algorithmic efficiency, right? Then results on benchmark problems. I'm going to give you some benchmark problems, training efficiency, and also CPU times. And I'm going to focus on quality control using machine learning and AI. I will, present only the machine learning part. It is mainly model identification studies using AI. It's a black box approach. I have no idea about glass manufacturing. It's a very energy intensive, chemical process, inorganic chemical process. The temperatures are 1400 Celsius. So it has fueled continuously energy consumer, you add 10% recycled glass. It also has a lot of component with circular economy, etc. And how do you identify a model? It's a difficult task. And it was a black box, and we even, at the operational level, we were able to identify the changes that were made and was not reported to us. Results and energy conundrum and discussion and conclusion. The way it is going, energy is going to, be a major consideration in AI. So why AI needs so much energy? And there are, according to ChatGPT version 5, there are two major stages. I knew this, but I validated it by ChatGPT as well. Two major stages. One of the stages is training, where we collect all of the data out there in the world. We collect all of the theses that you will be producing, papers, all of the literary work, Wikipedia, anything that you can find to train the AI system. Then inference is when you ask a question, what does these systems do, right? What do they do to answer your question? So two stages. Then deeper analysis of algorithms. What is the core algorithm here? How can we use AI for quality control of continuous processes, discrete processes? It is studied extensively in manufacturing sector, right? Quality standards by Baldwin, Japanese, etc. But continuous processes are not well studied. And we are going to present the results, and for AI part, we are still trading between or thinking the compromise between model predictive control or reinforcement learning. So these two algorithms are well known to you guys. So according to AI, ChatGPT works in this manner. At this training phase, it collects all of the data, text, data, video, images, etc. And also it preprocesses, it converts this video and text into digital information, and also it uses model training for establishing a model representation of the world as we see. So main algorithms are through transformers, and GPUs, TPUs are used to process this information. Then we have trained model parameters. Right? Model parameters are known. If you publish this, for example, ChatGPT published this in version 3, and all of a sudden DeepSeek came. Actually, DeepSeek received the trained models to establish the service, and there was a big commotion saying that the Chinese are much more efficient. But if you bypass this training stage, of course, you can be very clever, but the main bulk of the effort goes at the stage, model training stage, right? Then inference stage is servicing the user. User asks a question, what happens is you prompt, you say that, okay, answer this question for me, and this text is automatically converted by transformers into understandable, digital information. Then this train, there's a, connection between trained model parameters, and automatically it receives the data and gives you the output, right? So this is very similar to Google search, right? Google search, very similar, but the algorithms are much more complex because we have to, consider several hundred billion, parameters. So how does Google give us accurate information every search, current information? Because it goes through the internet every night, collects the information every night, and updates itself every night. For artificial intelligence case, it is not possible. Why? Because this is very intensive, humongous work here. That's why we have to wait approximately a year for new version of an artificial intelligence to come into play, right? So this is, again, somebody else's report, McKinsey, and according to them, projected US data center energy consumption, and according to this, currently in 2023, it was 150, terawatt hours of energy was required. And 2030, this will increase by 4 times, 600. Even at this pace, it will be much more, right? Because US wants to specifically keep this know-how and expertise on its own companies and soil. So it will be a little bit, steeper increase in energy consumption. So you can consider efficiency gain, but everybody is talking about efficiency gains in hardware. Nobody is talking about algorithmic efficiency. It is our job, actually, to address this issue, bring this discussion into the table. So AI adaptation, according to another study, mainly Europeans, so cost of training, the first generative AI in 2022 was $9 million in 2022. So in 2028, it will be $3.5 billion. So by 2036, you see, it will be equivalent to GDP of US. GDP of US is currently $30 trillion. $30 trillion is going to go into hardware and energy for training our AI models. This is getting out of control. Instead, we have a sledgehammer and a lot of money, a lot of resources, and we are pounding this sledgehammer to beat this problem. But, in our training, I was very lucky at Carnegie Mellon, only 5% of the faculty believed in supercomputers. 95% of the faculty taught us that, you have to design intelligent algorithms, right? You cannot rely on this brute force of the hardware. Of course, hardware is important, but, human intelligence is more important. So this is, right on the money. I'm going to show you again the projections. This is our work, our own work, which is under review right now. So we have several, scenarios, And considering computational complexity, demand for AI models and services in different parts of the world, and also computational demand and power consumption. And as you can see, we are just at the beginning right now in terms of AI, right? Maybe in this room, only half of you are using AI from time to time. Maybe one or two are using extensively. In preparing these slides, I used AI. I used ChatGPT a lot. I asked ChatGPT to prepare some tables. I asked the ChatGPT, how do you work? You represent pictorially, etc. So we are just at the beginning. So it is going to improve a lot. Industrial competition and other competitions. What is interesting is the energy consumption as percent of global energy consumption. So we have three scenarios. One of them is large language models. At this pace, it looks like only large language models will survive because a lot of investment is required. Only a few of them can still stand with the expenses and resources required. And some of them are more and smaller. More and smaller, it means that small language models that some specific domain experts are advocating. And according to this scenario, globally by 2050, 47.3% of energy demand globally will be towards AI, right? Then in the medium scenario baseline, the way the business as usual, 27.5% of global energy, and in the best case, 13%. Still, 13% is significant, right? But 47% is a lot, right? So where does this energy go? So according to different scenario, you see this blue triangle is training. Majority of the energy goes into training problems. The training is problems, and these training problems are becoming much more complicated. We can have business as usual or emission target scenario. In every case, training problem is the most dominant energy consumer. Then we have the usage. Usage means inference. When I ask a question, how do you answer? Right? A small inference. And also manufacturing costs. Manufacturing costs are also significant. Transportation is almost negligible. Logistics cost. Logistics and energy, for logistics. But manufacturing is also another important consideration. Efficiency in manufacturing. Okay. So let's consider the training problem. I hope so far I have been able to convince you that AI is very energy demanding. Majority of the energy goes into training problem. And let's look at the details of the training problem. So this is the foundation of any artificial intelligence-based methods that uses neural networks. Deep learning, artificial neural networks, transformers, etc. What you have is, you have input vector. Input vector, let's say you are doing a linear regression, and you have 10 parameters, 10 input parameters that is going to be mapped to one output parameter. What you need here is these parameter values plus their weights. What is the weight importance of this particular variable? And what you do is you sum all of these multiplied, this parameter value multiplied by its weight, and sum them up. And also afterwards, you have to have activation function, whether this parameter or this multiple is important in my output or not, defining output Y or not, right? So obviously, this is a simple representation. More sophisticated representations are here, but from statistics, even the most statistics perspective, most advanced and complicated artificial intelligence algorithm uses this simple regression mechanism. Simple regression mechanism. And if you go a little bit deeper, mathematically, this output matrix, I can define several outputs. Output matrix can be represented in this form. Here, F1 and F2 are activation functions, and also W1 and W2 are weight matrices for different factors. And why do we have W1 and W2? Because in artificial neural networks, we have the seen and also hidden layers. W2 is for hidden layer. F2 is for hidden layer. What is happening inside the output. And B1 and B2 are bias matrices if you want to create bias toward a particular input. So typically the training problem will involve solving this very simple unconstrained optimization problem. If I have n training data points, I want to minimize the deviation, right? And my problem is determine the weights and also bias values for each input and output pair. But this is a simple problem. Now, the question is, how do I solve this? The trick is to use activation functions because this multiple, right, is going to be activated or deactivated. If it is deactivated, output is going to be 0. If it is activated, it will be 1. And in order to represent this mathematically, people use the different functions. One of them is sigmoid function. It is the first one that is used extensively. Then we have tangent H function, which is a better approximation of this discrete nature. And we also have the ReLU function that is recently being used. And there are other variants of this, right? Softmax, etc., etc. But usually, all of these algorithms are at the core, or these models are at the core of algorithm, activation functions. So, state-of-the-art AI platforms like ChatGPT, Grok, Gemini, all of them use these. And let's look at the solution algorithm. So do you see a problem here, here? Maybe not here, but there is a discontinuity there, non-differentiable. But here you can see a problem. It is non-convex, right? It's a nonlinear non-convex function. And imagine that, in a minute, I will show a table that was prepared by ChatGPT. Imagine that I have billions and billions of such functions. That's why artificial intelligence takes so much time, because you have to manipulate billion parameters. So it's non-differentiable. You have to solve this, and still, again, this is information by ChatGPT. I asked ChatGPT, if I were to train my model in U as a small language model, which algorithm are you going to use? So gradient descent algorithm, and I asked him, could you provide the reference for this? And the reference is Cauchy 1847, the solution algorithm. I'm sure I asked this first design. I'm sure people tweaked it because it's an old, algorithm. But I have a lot of respect for Cauchy, one of the founders of applied mathematics, highly intelligent genius. But you say probably there's something better, or we could have done something better. Second algorithm suggested that second order or quasi-Newton method, I'm sure you have seen this in optimization, nonlinear optimization, or even nonlinear, root finding problem. So it is by quasi-Newton methods, and the design algorithm is by Fletcher and Powell in 1963. This is, according to ChatGPT, what it uses to solve it. First reference for these algorithms. Right? as you can, I mean, as optimization community, majority of you are doing modeling and optimization, numerical analysis, you will appreciate that, this is non-linear, non-convex function. So guaranteeing optimality is going to be easy when I have one or two of these functions. But if I have billions of these functions simultaneously, in that case, it will be a problem. That's why I'm using all of this infrastructure. I'm running the fastest computers, CPUs in the world to solve this problem, yet I cannot find the optimal solution. I cannot guarantee global optimal solution. If I want to guarantee global optimal solution or convergence of all of them, entire system, it will take forever. Therefore, I have to stop somewhere. That's why you ask ChatGPT a question today, tomorrow, in that case, you may get a different answer. You know that it's not trained. ChatGPT 3 has one trained model, ChatGPT 4 has one trained model. If different answer is given, it means that this not guaranteeing global optimality is the culprit here. Okay? All right. So hardware needed for training. So this is again prepared by ChatGPT, and GPT-3 in 2020 had 175 billion input parameters. 175 billion. Now think about the weights, determining weight and bias, and also activation function for this. You can imagine the complexity of computation. That's why I need, a training center or data center larger than this building, full with all of these expensive processors, right? So computing time is given in this form, and also they use approximately 1,000, A100 GPUs by NVIDIA. So state of the art. The last one is Grok, 270 billion input parameters. It's undisclosed, but unofficially it was told, it was reported that 20,000 GPUs were used to train this model, 20,000. And it took them approximately 3 to 4 months, somewhere in Appalachian Mountains, Tennessee, in the mountains. And it took them 3 to 4 months. 20 to 25,000 GPUs. Each CPU will cost you $250,000. That's why OpenAI is asking for a nuclear power station next to their building. It is the hardware requirement plus energy requirement plus the water requirement for cooling. So it is already getting out of hand. You see, 3 and 4 from CPU time, right? I mean, 100 times increase in CPU time, training time. You can imagine that 100 times increase in CPU time probably will reflect into 100 times, because algorithm did not change. Algorithm is the same, right? Maybe a few tweaks, but there's no foundational change. So GPT-5, undisclosed, but one order of magnitude increase, right? Probably this was 1,000, 10,000, maybe close to 50,000, 80,000, 100,000 CPUs, right? So this effort is completely relying on hoarding energy and using hardware extensively. Nobody is paying attention to algorithmic efficiencies. But at process systems engineering and operations research community, we always benchmark ourselves, right? Is my algorithm better than somebody else's algorithm, or is my algorithm better than my algorithm last year, right? So we have this mentality. So my approach to this problem is from this perspective as well. Could we do better, right? Global optimality cannot be guaranteed. It is well documented because stochasticity is introduced because you cannot guarantee convergence. So you stochastically you try to tweak and try to find a better initial solution so that you can converge to optimality. And also, you see, ChatGPT-4, you cannot use previous results. You see, you spend all this energy, all this equipment, all this infrastructure for 4 and 5, you start from 0. This is against human nature, right? I learned something, now I erase everything and learn from scratch again. But if I had 175 billion entry points, data points, maybe 250 billion here, maybe 500 billion here, I have done half of the work. Why can I not use, why these companies do not want to use this, recycle the existing knowledge? Why do they not do warm stuff? First, heavy reliance on hardware, right? Sledgehammer will do everything for us. Second, my algorithm does not give me global optimality, right? Maybe by different run, I'm going to get a different answer. Therefore, this is the main, reason. So every version needs more energy, more TPUs, more, water cooling, more of everything, right? So let's consider this tangent H function. So tangent H function is here. So the problem formulation, as we see here, this is non-smooth and non-differentiable. So I'm advocating or I'm proposing a piecewise linear approximation of this tangent H function. And it will be flexible. I can use 3 pieces, 5 pieces, 10 pieces, 20 pieces, whatever is required. And my value formulation is going to change a little bit, and it will become a constrained optimization problem, right? So these, since the absolute, value operator is discrete, I'm going to have this, right? Replacing absolute value with this, and I'm going to minimize this deviation. So the rest of the problem is the same. And here, I'm going to define these, loading functions for piecewise linear, and with this, I'm going to represent this problem as a piecewise linear function. Does it do better? Let's see whether it does better. And for this representation, I have 2 possible, formulations. One of them is unary, that was proposed by Jaroslav in 1984. So it has convex combination, and here binary variables are introduced for each interval, whether this interval is active or not, whether the other interval is valid, or binary that was recently proposed by Pablo Vielma and Nemhauser. I think many of you know the name Nemhauser, but Vielma was a PhD student at Georgia Tech, worked at MIT for 3 or 4 years, and afterwards he was snatched by Google. He's right now working for Google, and here it has a much better formulation in terms of formulation, but the performance, algorithmic performance, is weaker than unary. So special ordered set is a tool in mixed integer programming that we use extensively. So in this case, I formulate this problem as a mixed integer programming problem that takes advantage of the special ordered sets. And this is my simple algorithm to do the training algorithm. Right? I'm replacing this, Cauchy or quasi-Newton with this tailored special ordered set training algorithm. And in this case, let me illustrate this with a case study on an atmospheric distillation column that you are very familiar with. And distillation column has 27 distinct features like temperature, vapor pressure, heating duty, cooling duty, etc., at every stage. And in my setup, I am trying different neurons in the hidden layer and also number of piecewise linear segments that are used. And I'm comparing my performance with nonlinear programming problem. Many of you may know that it is Adam solver in neural nets that uses nonlinear programming problem. And I'm coding my Sussex algorithm. Again, my coding is very primitive. I implemented it in Python. So it's not very effective. I know that Python, any algorithm that is coded in Python is 30 to 100 times less efficient than an algorithm in C++. Therefore, I can say that, okay, I'm testing ideas. This is not commercial implementation and mixed integer programming formulation. So let's see the results. So in some run settings, we don't use any heuristics. We are using the Groby. We are using Groby only, mid focus. We are focusing on optimality. No heuristic, no warm start, no pre-solve. We are doing classical. Only we are implementing our own branch and bound algorithm that is tailored for Sussex, and MIP focus, and also NLP training is used as a TensorFlow Keras, right? And also MIP training is classical, the best of Groby, and number of neurons and piecewise linear segments are recorded. And also I have a CPU time for each run, CPU time limit. Okay, these are the results, comparative results, the optimal solution or profile on 175 distinct measurements on this atmospheric distillation column. As you can see, NLP, SOX, MIP, everything converges, very nicely, and I can, predict the vapor pressure. And as you can see, if I use actually normalized vapor pressure in my test, I see some deviation, especially the biggest deviation comes from green, which is the MIP solution because MIP could not converge. And in some cases, my SOX, right? NLP is a little bit successful, except for a few cases. So SOX, in this case, my number of my pieces are not sufficient to accurately pass the testings. So in that case, what I do is I increase the number of pieces. So I see improvement, but this improvement in my performance SOX is a lot of degradation in MIP solve. Why? Because MIP, with the given CPU time, was not able to train the problem accurately because it was not able to reach the optimal solution for the setting. And if you go a little bit further, in this case, what you see is, MIP is improving a little bit in terms of, the testing, but my SOX is starting to approximate very well the testing. So 5 neurons, again, similar problems, but if I go to 5 neurons in this 27 input, 1 output, training problem, I see that, my actually SOX is behaving very good. Means that 5 neurons at the hidden layer are actually sufficient to capture all of the intricate details of this 27 parameter model. And also you see strong deviation with MIP. So in this case, mixed integer programming was not able to solve this problem. Okay. So I have more of these. In the interest of time, I will pass these quickly. It's 16 neurons, 20 neurons, And in 24 neurons, I have seen the results accurately. And as you can see, I also do the training and testing side by side, and I can see that my algorithm is convergent. Let's see, as the number of neurons and number of pieces in piecewise linear approximation increases, I'm getting more accurate and also guaranteeing optimal solutions. So results. These are mean absolute errors. As you can see, I have NLP, MIP, and SOX. And in the case of SOX, I have seen in all of these cases 0 in the training phase. Right? Training phase 0 means that I was able to solve this problem optimality within the given CPU time limit. In all of the cases, no matter what the no matter the complexity of the problem, right? This is 30 neurons and 7 pieces. Moreover, for this problem, I achieved in the testing phase the best performance, 3.6% deviation with the SOX algorithm. So SOX achieves 0 training error. It means that training is globally optimized. So this will give me an opportunity if, let's say, I have a model with 175 billion parameters, and I want to increase the complexity, I can use these results if the new parameters are not affecting my decisions or my training models. MIP was not able to solve any of the training problems to optimality. That's why we have this mean absolute error. And NLP was stuck with local optimal solutions in all of the cases. And for the testing, SOX is superior to MIP in all cases. This is the main point. And SOX is better than NLP in 7 out of the 8 cases. So ADAM optimizer, it means that I'm also able to beat ADAM optimizer. NLP is better only when N is 3. It means that when neurons is 3, simple problem, NLP was able to train better. But the other cases, complex problem, complexities, mine is doing better. In terms of CPU time, and notice that this is log scale, right? So this is showing that number of neurons and number of pieces, my algorithm is scaling logarithmically, not exponentially, right? It's like a linear, right? It's like a linear function in cases. So I have tried this in many different data sets, distillation tower, wastewater treatment, cancer data, and house prices. In all of these cases, CPU time, this is the mean with 95% confidence interval, and these are the others. So it means that I was able to solve this problem scale-free almost, right? So with this, I'm able to show that training problem may have, this is the first work that we are doing, right? Yes, right. So in that case, SOX, I'm not saying SOX is certainly better. SOX has a better potential to be better. More research has to be done, right? More research has to be done. So, okay. So let's go to the quality control using machine learning and artificial intelligence. The glass making process is a very complex process where we prepare raw materials and we feed everything through a furnace or melting pool. And this basically homogenizes all of the ingredients at 1400 degrees Celsius. And after that, I withdraw this and shape the glass. And this is the furnace. It is the heart of the system. And in furnace, we have the burners that provide fuel. And also we have this arc on top of the pool that shields the heat. And also we have thermocouples, etc., pinhole and doghouse. It is feeding different exotic ingredients to change the color of the system. And this system has 185 tons per day capacity, production capacity. 185 tons of glass per day. It is one of the largest in the world, right? So this company is the largest glass producer of Europe, and right now they are building 2 glass manufacturing facilities in the US. So how do I control the glass? It depends on the ingredients and the conditions of the system, right? So what is important is, the ferrous oxides that are in the glass. When they are oxidized, their oxidation level determines the color. For example, it can be green, blue, or red. But I'm shooting for this crystal clear glass, right? White or unclear. But what happens is if it is too oxidized, it turns to green, this side, or yellow. And if it is medium, it is like transparent. And if it is reduced, it goes into blue spectrum. So it is my problem because I have this 185 ton material. You can imagine, your car glass door. They are also producing car glass. One of the car glasses is like $1,000, and it should not be more than 2 kilograms, right? So it is very expensive. If I mix the color, in that case, it will be very costly. And for glass, glass spectrum is measured by 3 parameters, L, A, and B, and operational data on 2-dimensional projection of this system is this. So their system is inclined for blue, but this system has to be trained for every furnace separately. Probably blue. Blue means what? Blue in the previous slide is reduced. Means that I'm feeding more oxygen into the system. It is reducing more. So probably there is a systematic or design or operational problem that I have to address, because obviously the most value is going to be here or around here. This is the most transparent. So first, in this work, we want to identify what controls the color. Is it temperature? Is it the fuel-air ratio? Is it the ingredients? I'm adding a lot of exotic ingredients, right? So what changes the color? And as you can see, this is going to European market because it is crystal clear, right? This is going to 1/10 of the price to probably Africa or Asia, right? 1/10 of the price, cheaper markets. Same product, same ingredients, same everything. It is only I'm not able to control my process properly. That's why I'm losing tenfold value out of my product. It's an important problem. So methodological approach. First, we collected data. We did the machine learning work, and results are obtained. And we also did the model selection. Here is the data. Right? So this is the date of measurement, and X value, Y value. These are masked by the company, and L, A, and B values that controls in 3 dimensions the color spectrum. And this is the iron 2 plus, and this is the ratio of iron to ferrous oxide, and also the other ingredients like sodium sulfate, cerium oxide, cobalt oxide, and zinc, selenite. Other measurements include the temperature region. You see 1500 degrees Celsius, etc. So it's very energy intensive, and others, right? So natural gas consumption, per hour, all of these inputs. So we have approximately 50 inputs coming every millisecond to our system, the machine learning system. Every millisecond, these sensors are sending data, and some of the data, like lab measurements, are coming once a day. Okay. So seasonal behavior is automatically detected. So we saw that outside ambient conditions are also winter, summer is changing the process characteristics because maybe it's something to do with the air pressure, right? Or partial pressure of oxygen. And also, moreover, we said that considering this, in order to obtain an accurate model, we are going to have an automatic detection of the model change, like discrete models, like disjunctive. For example, if I'm in the month of, let's say, winter months, this is going to be my model. Automatically, I will see it is changing to this or not. Okay. And these segments, as you can see, different algorithms were tested, and we have identified the best performing, system. And best performing system is, segment, and this is our R square value, right? So as a summary, this problem is a significant problem. One of the biggest difficulties for second phase, which is application of the control algorithm, design of the control algorithm, is, we have an accurate model, but the problem is time lag. This furnace is, this pool is 180 tons of molten glass. You add something, you observe the effect of this only 4 to 8 hours later. Means that 4 to 8 hours, you sit and wait whether it is going to come out right or not. In the meantime, you have wasted millions, right? A lot of energy. So we have to overcome this problem. Seasonal behavior. Environmental conditions have a strong impact because oxygen ratio and impurities in air. Equipment performance. What happens is these furnaces are torn down every 5 to 10 years and rebuilt from scratch. Because performance degrades, imagine 1500 degrees Celsius, 24 hours, 7 days, even the bricks, right? Thermal bricks will not sustain this. So it is, and if it is very new, you have a different, operation characteristics. If it is very old, it's a different. So it's, your machine learning model becomes very complicated in this case. So right now we are not finished with the work yet. Model identification is finished, but we are considering MPC and reinforcement learning, whichever works. Reinforcement learning is certainly data-based. MPC is model-based, but we believe in our model. We will see what happens. So this work has been a joint work with Erdal Aydın, Assistant Professor of Chemical and Biological Engineering at Koç University. İpek Pehlivan is my master's student. Ece was a PhD student. Actually, the first part of the work was done during my course, integer programming course at Koç University. She was a student there, and I usually give students a term project. She said that, give me a project. I told her this project, and she was very diligent, followed up, and it resulted in a very important work for me. And Kiran is a PhD candidate who does the majority of the work. Okay. Thank you very much.